Welcome to the deep dive.
Okay, so let's unpack this. You want to specialize a powerful large language model, let's say for advanced medical knowledge. But standard supervised fine-tuning, or SFT, often comes with this really steep price. It's called catastrophic forgetting. Basically, the model forgets its general knowledge.
And what's so fascinating here is the contrast. Yeah, SFT, well, it degrades those general capabilities, but on-policy reinforcement learning, RL, it actually preserves them. We're diving into the mechanism that explains this discrepancy. It's something called the confident conflict.
Mm.
Our mission today is to really understand this conflict and explore a new solution for it called entropy adaptive fine-tuning, or EAF.
Okay, the confident conflict. I like that name. So there's this distributional gap, right? RL data aligns with what the model already believes, but SFT is, well, it's forcing the model to fit some external supervision.
Exactly. And that mismatch is where it gets really interesting. It creates these confident conflicts.
So these are tokens where the model is not just wrong, but it's very confident that it's right. That's the core insight. These conflict tokens have a low probability according to the new data, but critically, they have low entropy. And low entropy just means the model is highly, highly confident in its current prediction, even though it's the wrong one.
So forcing it to learn the new ground truth in those moments.
It triggers these massive destructive gradient updates that just overwrite its general knowledge.
I love the analogy in the research. It's like forcing the model to label a ball as a truncated icosahedron. The model is absolutely certain it's the ball. That's the low entropy. But the label forces it to learn this very complex term it thinks has a low probability.
And that's the fracture point. They even ran a pilot experiment that confirmed this.
Oh, really? What did they do?
They just masked the tokens that fell into that zone,
Sorry.
low entropy, low probability. And it significantly mitigated catastrophic forgetting.
Wow.
It proved that those specific conflicts are the main driver of the degradation.
So that brings us to the solution then. EAFT. How does it fix this?
Well, instead of just relying on the prediction probability, EAFT uses the token's own entropy as a sort of a soft gating signal. It modulates the training loss.
A soft gate. So it's deciding when to push hard and when to back off.
Precisely. It lets the model differentiate between its own rigidity and genuine uncertainty. When the model is being stubborn, low entropy, low probability EAFT suppresses that conflicting gradient. It's called conflict suppression.
So it protects what it already knows well.
Right. But when the model is uncertain, which is high entropy, the loss stays high.
And that's for effective adaptation. That's the knowledge acquisition part.
You get the best of both.
The research says this leads to a Pareto improvement. Right?
Yeah.
EAFT matches or even beats SFT on the target domains, math, medical, whatever. But it does that while preserving general capabilities.
The numbers are pretty stark. In the experiments on the Quen 3-4B model, the drop in general performance for EAFT was only minus 1.0.
And for standard SFT.
Minus 4.6. A huge difference. It just holds on to its skills so much better.
So what this all means is we found a simple, computationally efficient way to stabilize specialized LLM training.
And it is efficient. They use a top 20 approximation for the entropy, so there's almost no overhead.
And it works by respecting the model's existing high-confidence knowledge.
Yes. This approach is fantastic for domain adaptation. It really excels there.
Yeah.
But it does raise an important question.
Go on.
Well, EAFT is designed from the ground up to resist these conflicts, to protect general knowledge.
Right, that's the whole point.
But what happens if the SFT task specifically needs what we call knowledge editing? I mean, what if you're trying to correct an outdated fact or teach a true counterfactual that the model is very, very confident about?
Right.
In those specific cases, EAFT's resistance to overriding those prior beliefs, well, it could become a limitation. It might actually hinder the update you need to make.
Okay, let's get into it. We all look at those LLM leaderboards, right? The lists that tell us, Model X is better than Model Y.
Right, and we basically take them as gospel.
We treat them as unshakable truth. But here's the question we're digging into today. What if the test itself is just flawed?
And that's exactly what the BENCHMARK2 framework is all about. It's forcing us to check the quality of the yardstick, not just the thing being measured.
Yeah, because the sources point out three huge problems that are, lurking just under the surface of these rankings. The first one is pretty obvious.
Ranking inconsistency.
Exactly. You have Model X beating Model Y on benchmark A, but then on B and C, it's the total opposite. You get three different stories from three different tests.
It's chaos. And then the second problem is what they call low discriminative power.
Which basically means the test can't really tell the models apart.
Yeah, precisely. Imagine a test where, like, the best model gets a 90% and the worst gets an 88%.
All the scores are just clustered together. It's useless for comparison.
And then there's the weirdest one, the one that feels like a bug in the matrix.
Rank inconsistent items. This is where bigger, supposedly smarter models, say GPT-4, fails a question.
That its smaller, weaker sibling, like GPT 3.5, actually gets right. It just shouldn't happen.
So how does BENCHMARK2 even begin to fix this mess? It introduces 3 new metrics.
It does. It starts with the big picture. Cross-benchmark ranking consistency, or CBRC.
Okay, so what is that checking for?
It's basically seeing if a benchmark's ranking of models agrees with other benchmarks in the same field. You want high agreement, right? Something over 0.7 or 70% to feel confident the results aren't just a fluke.
Got it. So that handles the conflicting stories. But what about that clustering problem you mentioned?
That's where the discriminability score, or DS, comes in. It actually measures the score spread.
So make sure there's enough room on the scoreboard to see a real difference between the top and bottom performer.
Exactly. You're looking for a DS score above 0.4. If you have that, you know the test is actually spreading things out in a meaningful way.
All right, now let's get back to that bug in the matrix. The rank inconsistent items. That's tackled by the third metric, right?
That's right. Capability Alignment Deviation, or CAD.
And this one is interesting. It sort of assumes that within the same model family, bigger should mean better.
It does, but it's not circular reasoning. Think of it as a diagnostic tool. We use that known trend that larger models are generally more capable to find the flawed questions.
Oh, I see. So if a question breaks that rule, it's the question that gets flagged, not the model.
Precisely. CAD penalizes those specific items. You're looking for a high CAD score, something above 0.6, to show the test questions are well designed.
And when they applied this whole framework to, 15 real-world benchmarks, the results were kind of alarming.
Oh, definitely. It showed a huge variation in quality. For example, a math benchmark, AME 2024, did great. It had a really high DS and a strong CAD.
So it's good at telling models apart, and its questions are solid.
Exactly. But then you look at something like Psycho-A, which is for social intelligence.
It's a pretty critical area.
A very critical area. And it was just problematic across the board. The CAD scores were consistently low, around 0.20 to 0.27 for every model family.
Wow. So that suggests the test itself, the questions we're using to measure social reasoning, are maybe just inherently flawed.
That's the strong implication. And it points to this big trade-off they found. It's really hard to find a benchmark that has both high discriminability and high capability alignment. They rarely seem to go together.
But the framework offers a solution here, a really practical one. Selective benchmark construction.
This is the really exciting part. They used CAD and DS to filter out all the bad, noisy questions from existing benchmarks.
And by doing that, they built these smaller, more efficient tests. They got a ranking consistency of 0.93,
which is incredibly high,
while using only 35% of the original data.
35%? I mean, that could change the economics of model development overnight.
It really could. The takeaway seems to be that high-quality benchmarks need a careful balance.
Yeah.
You can't just throw a million questions at a model.
No, you can't. Developers should be aiming for a DS above 0.2 and, more importantly, a CAD above 0.6. Those should be the new minimums for quality.
Absolutely. And that leads to our final thought for you to chew on. If we can get the same or even better evaluation quality from just a third of the data, what does that imply for the speed and the cost of building the next generation of truly massive language models? Okay, so when we think about AI agents, we always jump to this amazing end result, the invisible concierge that books your whole vacation with just one command.
Right, the magic wand.
But that story, as charming as it is, it completely skips over the absolute mess of engineering required to actually make it happen.
It really does. I mean, before an AI can book that flight, it has to navigate hundreds of tiny failure-prone steps.
What do you mean by that?
Well, think about the websites you use every day. Legacy interfaces, pop-ups, forms that just silently reset themselves.
Oh, I know those. Or calendar widgets from, 10 years ago.
Exactly. These systems are so inconsistent, so the AI has to become this master debugger just to get through a simple task.
So this deep dive is really about the necessity of the mundane, then.
Yeah.
All the hard work needed to master these fundamental, almost atomic behaviors.
The atomic behaviors, yeah. We're talking about teaching an AI to literally scroll correctly, or to know a calendar from a drop-down menu, and to enter data into a form exactly once.
Not twice.
Right, without double submitting and buying 2 plane
So
tickets.
the researchers have a name for this, right?
They do. They call them norm core agents.
They're norm core.
Yeah, the goal is kind of counterintuitive. You're training these incredibly advanced systems to be exceptionally good at the simplest, most boring interactions that make software actually work.
It's kind of funny. The AI that can think strategically has to go back to digital kindergarten.
It really does.
So how do you even practice that? You can't just let them loose on live airline websites, right?
No, you'd crash everything. They've built these high-fidelity reinforcement learning gyms, RL gyms.
Okay, so like a simulator.
Precisely. They're controlled sandboxes designed to be just as messy and broken as the real web. The agents they practice over and over, often in scenarios that are built to fail.
And the standard for success here must be incredibly high. I mean, if these agents are making payments or changing a database,
Oh, the standard is absolute. It's a lot like the mindset for self-driving cars.
where almost right is just wrong or unsafe.
It's completely unsafe. Reliability is non-negotiable. And that brings us to the core of it. If you can't trust the UI, what is the real source of truth?
It has to be the database state itself.
You got it. They use formal verifiers as the ground truth. These tools ignore everything on the screen, the clicks, the animations.
So they just look at the raw data.
Exactly. Every task is tied to a spec that defines the required end state in the database. And crucially, what must not have changed.
Can you give us an example of that?
Sure, take send an email. The agent clicks send. Success isn't that click.
Or the little message sent banner?
Nope. The verifier checks the database and confirms, is there exactly one new email record? And were no unrelated records touched? That rigorous check is the only reward signal the agent gets.
Wow. So let's talk about the actual workouts, the norm core workouts. What's the first one?
The calendar stability test. This one is all about UI drift.
UI drift. You mean when you go to click something and the whole page shifts?
Yeah. That's the one. It trains the agent to handle components that move or even disappear and then reappear mid-click. It has to stay locked on target and commit the date just once.
Okay, and then you have the drop-down discipline drill.
Yeah, this one's critical. It teaches the agent to ignore what it sees on the surface.
How so?
Sometimes you'll select an option and the menu looks like it updated, but the backend is lagging. It hasn't actually registered the change.
Right, like a loading spinner that just keeps spinning.
Exactly. This drill teaches the agent to wait and trust only the verified system state, not the immediate visual feedback.
And the last one is the async endurance run. That sounds intense.
It is. This is for long workflow searching, then filtering, then validating, all across multiple pages.
Where things can break at any step.
Right. Backends can throw errors, pages can load out of order. The agent has to maintain its goal, its coherence, across dozens of these fragile little steps.
So to wrap this up, what's the big takeaway here for you listening to this?
Well, I think the core idea is that building truly useful AI agents, it's not about some magical general algorithm.
It's about solving 1,000 tiny, boring, but incredibly hard reliability problems.
Problems that come from interacting with the digital world we've already built.
So it's a powerful foundation, but it also shows just how much work is left to do.
Yeah.
The source material also mentioned these other massive research areas, automated reasoning, quantum tech security, and privacy. And that leaves us with a final thought for you to chew on. If just mastering how to scroll reliably is this difficult, what are the foundational atomic behaviors that an AI will have to master for those fields? All right, for today's deep dive, we are tackling a big one, OpenAI's newest announcement.
ChatGPT Health.
Exactly. And this isn't just some small update. It's a whole dedicated feature, and it's aimed squarely at, well, some of our most personal information.
And the scale is just, it's pretty wild.
It is. The sources we've looked at show over 230 million people are already asking health questions on ChatGPT.
Every single week.
Every week.
Yeah.
So this product is really a response to a demand that is already there. Our mission today is to unpack what this is, what it promises, and crucially, the warnings that come with it.
So the first thing to understand about ChatGPT Health is the architecture. It's all about separation.
Like a walled garden for your health chat.
Exactly. A ring fence. It's designed as a completely isolated space, so your sensitive health conversations are kept separate from all your other, standard chats.
Okay, that makes sense. A security baseline.
It's the absolute minimum for handling this kind of personal data.
But wait, if it's completely ring-fenced, how does it maintain context? The example they gave about marathon training. That seems to cross the streams a bit.
That's a really sharp question, and it's a critical distinction. The system maintains context, not the confidential health data itself.
So it knows I'm a runner, but not my cholesterol levels from another chat.
Precisely. And the CEO of applications, Fujisumo, was pretty clear about the motivation here. She positioned this as a direct response to, well, existing problems in healthcare.
The big ones: cost, access.
Right, crippling costs, doctors who are overbooked, 6-month wait times for a specialist, no continuity of care. I mean, if your doctor changes every year, an AI that actually remembers your history starts to sound pretty appealing.
And that marathon example really brings it home. If you've been talking about training in your regular chat, the health section knows you're a runner when you bring up, say, muscle soreness.
It connects those dots. It pulls in that surface level context to be more useful without, breaching the core health data silo.
Okay, so let's talk about that data, because this is where it gets really ambitious. It's not just about conversations, it's about integration.
Yes, connecting to your existing wellness world.
The sources specifically call out some big names: Apple Health, Function, MyFitnessPal. So it can pull in your actual medical records or your fitness app data. How does that even work securely?
Well, all signs point to a secure opt-in API integration. It has to be.
Meaning you have to explicitly give it permission.
You have to grant permission, and that transfer has to be encrypted. But the key part is what happens after the data is in the system. And this brings us to OpenAI's single biggest promise:
The training data.
the training data. They state very explicitly that they will not use health conversations or any of that integrated data to train their models.
That's a huge deal. That's the foundational promise for anyone worried about privacy here.
It is, but that shifts the problem, doesn't it? It moves from a question of privacy to one of fidelity. Can you actually trust it?
Right. Can a machine that's built to predict text actually give correct medical advice?
And that's the fundamental challenge. An LLM works by predicting the most likely next word. It doesn't have a concept of truth.
Which is where hallucinations come from.
Exactly. It can generate something that sounds incredibly plausible, even authoritative, but is just medically wrong.
But hold on, what about those studies we've seen? The ones showing that some fine-tuned models can actually outperform doctors in certain diagnostic tasks. There seems to be some real utility there.
There is utility, but that's the legal tightrope they're on. The potential is there, but the reliability isn't guaranteed. And that's why OpenAI has to protect itself.
The disclaimers.
The disclaimer, it's right there in their terms of service. Our sources highlighted it. The AI is, and I'm quoting, not intended for use in the diagnosis or treatment of any health condition.
So legally, it's a co-pilot, not the doctor.
It can't be the doctor.
So we're left with this real tension. On one hand, you have this massive, clear desire for easier, more continuous access to healthcare. And on the other, you have the very real risks of using a predictive AI for something as critical as a diagnosis.
A huge trade-off.
And that brings us to the final thought for you to mull over. When you see a number like 230 million people already turning to this technology every week, what does that incredible demand really tell us about the state of traditional healthcare today? And with the company's own stark warnings in mind, what trade-offs, really, will people be willing to make for the sake of convenience?